So in this tutorial we are going to talk about the quicksort algorithm, and in the series of sorting algorithms we have covered the merge sort algorithm, which has a time complexity of big O of n log n, and the time complexity of this algorithm quicksort is also big O of n log n. So basically it is much more better than the merge sort in space complexity. So in merge sort, if you remember, in merge sort what we were doing is we are dividing a particular array into two equal halves, and we are actually storing those two sub arrays into left and right arrays. So we were allocating those sub arrays into the memory. But in case of quicksort algorithm, we are not going to do that. We are going to follow the divide and conquer strategy. This divide and conquer strategy in quicksort algorithm also, but we are not going to store the sub arrays during recursion. So the basic idea of quicksort is it's just that you will have to just pick up any element from this unsorted array, and you will mark it as a pivot element. So in this tutorial we are going to consider that we are taking the highest position as the pivot element. So we know that the indexing starts from 0 till end, so we will assign 0 as the low position, and this is the n minus 1 position or the size minus 1 position, and we will assign it as high. So basically in quicksort function we will pick up a pivot element, and we are going to just pick up each and every element of the remaining subarray, and we are going to do the sorting work in such a manner that all the elements which have values lesser than this pivot element are going to come at the left hand side of this pivot element, and the values which are greater than this pivot element are going to come to the other side. So what we are going to do is we will just assign this. We are just going to change the values of the low and high, or let's suppose I will just mark it as start and end for to make it more simpler. So I will make it as end. So what we are going to do is after the first pass, or after the first iteration, the array will look like this. So what we are just going to do is we will just assign all the elements lesser than 70 on the left hand side. So we know that 10 will come here, since 10 is less than 70, then 30, and then you can see 40 is also less than 70, 50 is also less than 70, and now we have no element which is greater than the pivot element. So we are going to write the pivot element here, and then all the remaining values which are greater than this pivot element are going to come to the left hand side of this pivot element. So the remaining values are 80 and 90. So what we're just going to do is we're going to call the quicksort function again and again on this. You can see that we have rearranged this array. So initially our unsorted array was like this, and what we have done is we have done a partitioning of this whole array around the pivot element. So we will create a function which is the partition function, and the task of this partition function is very simpler. It will just rearrange our unsorted array in this manner. So after this pivot element the partition function will give us the p index, which is the partitioning index, which basically means that this is the index position at which we have done the partitioning of this array. So this is indeed a divide and conquer algorithm, because we are actually dividing our array by picking up a single element and dividing it into two sub arrays. So basically we will just do some programming in algorithms so that we will change the value of start and end in such a manner that the quicksort function will start dividing it into sub arrays while partitioning the whole array. So it will not assign the sub arrays in different arrays like we were doing in the merge sort function. We were assigning the sub arrays. So in this case, this one is also a sub array and this one is also a sub array. So basically the partitioning function has divided this array into two equal parts, but it can be seen here that it is dividing the sub array. It is not actually dividing the whole unsorted array, it is just changing or swapping the values, and this is an algorithm which just swap the values in such a manner that the values lesser than this pivot element comes to the left and the values greater than this pivot element will come to the right. So in this manner quicksort will be called again from the start position to the p index position, and so what it will do is it will again do the partitioning, and when we will call this quicksort function on this subarray, it will again create it will assign the highest element as the pivot element, and again it will just swap these values in such a manner that 50 will come here and the values lesser than 50 will be assigned before it. So it is actually going to divide our whole array, but in a logical manner, not like the merge sort. We were storing these two subarrays, the right and left subarrays, and then we were rearranging them by merging them. So in quicksort we're not going to do that. So first we will call the quicksort function on the start position till the p index position, and we will also call this quicksort function from the p index plus 1 position till the end position. So we are going to call this quicksort function on both of these parts of an array. So we will again call on this when we will call this quicksort function on this subarray, it will again pick the pivot element. So basically the pivot element is assigned as the array end position, and what it will do is it will pick up the element at the end position of the subarray, and remember that the subarray is we are not actually storing it in the memory in a left array. We are actually going to move this end position to the p index position. So just by manipulating the starting and ending of the of this unsorted array, we can call the quicksort function again and again, and it will pick up the pivot element and it will start it will just start doing this like all the values lesser will come to the left hand side and the values greater than will come to the right hand side, and it will do it will do it again and again, and a moment will come when there will be only, so when we will keep on dividing this, then this is the pivot element which we have taken in this step. So in the next step it will pick up this one as the pivot element, so it will divide all the values greater than this element will come here and lesser than will come here. So this is another subarray, and this is also a subarray. So we will call this quicksort function until and unless the value of start becomes greater than equal to the end position, or we will run this quicksort function which will just recursively do this partitioning of the array until and unless the value of start is less than end. So if the value of start is less than end, then we are going to run this quicksort function, which will call this partition function, and it will keep on partitioning the whole array. And remember, it is not going to do the actual partitioning of the whole array into two subarrays. It is just a logical way of showing that it is working in this manner, but the quicksort function is just it will just change the start and end position, and it will keep on rearranging these elements in the original array. So this one is the original array, and it will just keep on changing the start and end position, picking up the pivot element and rearranging these elements, and after the value of start becomes equal to the end, it will just stop, and at that moment our array will become sorted. So this is a pretty intuitive quicksort algorithm, and it is used in most cases. So in most of the libraries, native libraries, quicksort function is used because it is much efficient than the merge sort algorithm, since we can also choose this pivot element as any random element, which will make this algorithm much more efficient. So now let us implement this quicksort algorithm in the text editor. So you can see that here I have created, so we will create an array. So let's suppose this is our array, and since we are using, okay, so we will take this array, and then we are going to call the function quicksort, which will pass the array, the start position of the array and the ending position of the array, and this is just printing of this whole array. So let's implement the quicksort function now. We know that the quicksort function will just run if this base condition is true. So start should be less than the end position. So if this condition is not true, then the quicksort function will not divide the array. So this base condition, this one is necessary condition, because if you will not implement this condition, then what is going to happen is the quicksort function will do the partitioning or rearranging the values infinitely. So this will become an infinite recursion. So you will have to stop recursion at this moment when start is less than end. So let's now create a p-index variable, and what we are going to do is we are going to create a function, partition function, and the partition function is responsible for giving us it is responsible for rearranging the array in such a manner that the pivot element will come at the p-index position. So it will return the p-index position, which is the partitioning index position from where our array is partitioned, and the task of partition function will be to rearrange this array in such a manner that all the values less than this pivot element will come on the left, and else it will come on the right hand side. So a partition function will take these arguments. We will give the array, the left position and also the right position. So these are the three things that I'm going to give to the partition function. And what will happen after we will get this partition index? We are going to create a recursion. This quicksort function will call itself again, and we will provide it with the array. And first we want it to partition from the start position to the index position. So I will give the value L comma P index. Then we know that now we will also have to call this quicksort function recursively on the right subarray also. So I will give the array and P index plus 1 position and also the right position, which is also the end position. So our quicksort function will go on recursively on this left part and also on the right part. So this is for the left subarray and this is for the right subarray. And it is actually this P index is the partitioning index, which is actually showing that it has rearranged this array. So the main task of this quicksort function is the partitioning, which is a little bit trickier. So this is the quicksort function, and after this we are now going to study the partition function. So let's now write this partition function, which is actually going to rearrange the array, and it will also return the partitioning index. So this time it will be int value. So the partitioning index, so the partition function takes the array and it will also take the low position and the high position. So now what we are just going to do is we are going to create a variable named pivot, and this since in this example we are assigning the pivot element as the element at the last position of the array or any sub arrays that we will encounter. As you can see here, it is the array highest position. So we have created a pivot element. Now what we're just going to do is we are going to create a variable int I, which has value low minus 1, and I will tell you in a later bit why we have assigned I as low minus 1. So now we will create a for loop which will run from int j equals to low position, and it will run until and unless the value of j is less than equal to high minus 1. And the reason why it is high minus 1 is because we will have to rearrange this array or the sub array. So it is actually high minus 1 value. So because this is the pivot element we have taken. So now we are going to increment the value of j after each iteration. So in this for loop, what we are just going to do is we're going to run an if condition, which is the comparison, which will compare the array, the value at the j position should be less than equal to the pivot. So you can see that the pivot element is 70 in this case. So let's suppose the value of j initially is 0, because low is 0 actually. So j is pointing to the to this value 10. So now we are going to compare this value with the pivot element. So if it is less than or equal to the pivot element, what we're just going to do is this I value is low minus 1, low is 0, so I is initially minus 1. So what we're just going to do is we are going to write this I plus plus, and I plus plus basically means that first you will have to use this value of I, and after it will be used then we are going to increment the value of I by 1. So basically this value I is the partitioning index. So what we will do is we will do two things. This I, we will return this value I, which is the partitioning index, and it will get stored in the P index, and then Quicksort can proceed by doing this recursively, as you can see here. So this value of I initially is low minus 1, which is 0 minus 1. So I is equals to minus 1 and not 0, because we don't know whether the first element or the element at the 0 position should be the partitioning index or not. So that's why we are just we have just marked this value I, which is the partitioning index, and initially it is set to minus 1. So whenever, what we are just going to do is, whenever we are going to run this this for loop, and this for loop will run from the j low position, j will run from low position to the high minus 1 position, and at each time you are going to move to the next element, what we are just going to do is you are going to compare it with the pivot element. So whenever you will get this condition which says that the value at the j position is less than or equal to pivot, that means that it should be at the left hand side. So whenever you encounter an element which is less than the pivot element, you are going to swap it with the value at the j position, and you are going to increment the value of I. So let's suppose initially I was equal to minus 1 and j was equal to low, which is 0. So you can see that at the 0 position 10 is less than pivot. So what you are going to do is you are going to swap the value at the I position with this j position. So now we will also increment the value of I by 1. So the value of I will now become equal to 0. So now our partitioning index is pointing to this position. So we will increment in the next iteration, we will increment the value of j. So j is now pointing to position 1. Again we will compare this element with the pivot element, and since the condition is not true, we are not going to increment this partitioning index, because we know that if we will increment the partitioning index, it will violate the rule of partitioning. So the partitioning index will always be I plus 1. So the next position will be the partitioning index, and this is the value of I. So I'm just going to write I here. So the basic idea is we are going to move this position I position only if we will encounter an element which is less than the pivot element. So what will happen if we encounter that this element is not less than this pivot element? We are just going to increment the value of j, and whenever we will so let's suppose j is now equal to 2. 2. So if the j is equals to 2, so now j is pointing to this position. So we know that 30 is less than 70. So what we are just going to do is we are going to increment this partitioning index, but before that we are first going to swap these two values. So first, that's the main reason we are not going to use the plus plus I, we are going to use the I plus plus. So first we are going to swap these two values, and then we will increment this partitioning index. So 30 will come here and then 80 will come here. So now this I will now point to this position. So the array will now be 10, then 30, then 80, then 90, 40, 50 and 70. So this will become our new array, and the position of I is now pointing to the first index, So I is equal to 1 now, and so I is now pointing to this position, and j was at this 2 position, and we will increment the value of j by 1. So now j will come at this next position, and it will again compare this value with the pivot element. So we know that this 90 is not less than or equal to pivot element. We are going to move j by 1. So now j will be equal to 4. So now we will see that this 40 is actually less than the pivot element. So what we're just going to do is, we know that I is now going to point to this position 1. This is the pivot element, and j is pointing to 4. So what we're just going to do is, we are going to swap the values at the I and j position. So we are going to swap the values at I and j position. So the value of this 40 will come at this position, which is this one, 80, and we will increment the value of I by 1. So now this partitioning index will come here, it will become 2. So these values are will get swapped, and this will go on and on until and unless we arrive a position when all the elements, when we will not encounter any smaller element than the pivot element. That is, the for loop will run, will compare this all the elements at the j position with the pivot element. So whenever this will be less than the pivot, we are going to swap it, and then we are going to increment the partitioning index. So in the last step, we will get this array, and I will be pointing to this position 50. So we are just going to return I plus 1 position, which is the partitioning index position. And since we are using this swap function, this swap function has already rearranged the array. So in this manner, we can rearrange, or we can do the partitioning. So we know that when this value at the j position is less than, so first we are going to do the swap. So for swapping, I will just create another variable here, which is the temporary variable. So first what I'm just going to do is, I will assign the temporary variable as array I position, and then I will assign the array I position as the array j position, and finally I will assign the array j position as the temporary position. So we will do the swap. So you can see that whenever we will assign the value, or we are going to use the value I, it is going to swap first, and then it will increment the value of the partitioning index. So this for loop will go on and on till the highest position, and it will keep on swapping whenever it will encounter any element lesser than the pivot element. And so we know that the pivot element will remain at the last. So this 70 is not here, it is actually at the last position, which is the 70. So this was 70 at the last step, and 90 was here. So after running this for loop, our task is to change, to swap these two values, so that the partitioning index will come at this position. So what I'm just going to write here, after this for loop, we are going to swap. So I will use another variable t here to do the swapping work. So what I'm just going to do is, I'm going to swap the value at I plus 1 position. So this is I plus position, I plus 1 position, and the array I plus 1 position will be equal to the array high position, which is the pivot element. So we will swap the partitioning index, which is the p index, with the highest value, which is 70. So highest is basically the pivot element. And in the last step, what we're going to do is we're going to assign the highest element as t, which is the temporary variable. So in this manner, we have created the partition function, and finally we're just going to return the partitioning index I plus 1. And now the quicksort function will use this partitioning index to do this rearranging again and again until and unless the start is less than end. So this is the whole program, and I have already given the whole program, the whole code in the description, so you can check it out. So thanks for watching. So let me just run this program here. So we have encountered this error. So start was not declared in the scope. Okay, so this should be L and this should be R, and this is in base condition. And you can also see that I have written p index here. It should be p index minus 1, since we are going to do the partitioning from the previous index. So p index minus 1. So let's now run it again. So now you can see that in the output we have got the sorted array. So this is basically the quicksort algorithm, which is much more efficient than the merge sort.